Okay, we have made it to the last section in Unit 6 for AB Calculus, and we are going to continue volume, but in this case we're actually going to calculate volume by discs and washers. So what you need to think about is when you have a disc and when you have a washer, and a disc is actually solid like this, okay, and there's no hole in the middle. A washer actually has a hole in the middle, and I'll talk about that in a few minutes. So, solids of revolution. Okay, a solid of revolution by definition is a solid that is generated by revolving a plane region about a line that lies in the same plane as that region. And this line that you're revolving this solid around is known as the axis of revolution, and I'm going to abbreviate that as AR. Okay? And many of these familiar solids are of this type. So I'm going to go through some familiar solids and we'll just take a look. So first of all, to determine if you have a disc or a washer, your solid that you are revolving around the axis of revolution is going to be adjacent to that axis of revolution. So in this case right here, this is my axis of revolution. Okay, and what we're going to do is we're going to take this rectangle and we're going to revolve it all the way around. Okay, and it is solid, so when we do that, it will create this right circular cylinder right here. And that's what is formed by this rectangle. But in this case, this is known as a disc, okay, because it's solid and there's no hole in the middle, because the shape is adjacent to the axis of revolution. Okay? So here we have a semicircle, and in this case the semicircle will be revolved around the axis of revolution. So here's my semicircle like this. And if you notice again, your semicircle is adjacent, meaning it is touching the axis of revolution, and we are going to revolve it around, and that gives us a solid sphere. So that will be totally and completely solid. Our last shape here that will be adjacent to the axis of revolution is a triangle, which once this is revolved all the way around the axis of revolution, 360 degrees, it creates a solid cone. Okay, so all three of these right here are discs. There is no hole in the middle. Okay, it is completely solid. Now, here, this is known as a washer, because if you take a look, there is a hole in the middle right here, and our solid is not touching or adjacent to our axis of revolution. There is a space in between. So here's our axis of revolution. This would be our revolution right here. But here we have space, which will create that hole, okay, or that hollowed out region. So in this case, what we end up with is a circular cylinder, but it's going to have a hollowed center. Okay? So it's important that you understand the difference between those two, and you need to be able to figure that out. Now, keep in mind too, this space that is created when the figure or the shape is not touching the axis of revolution, it could be just a teeny tiny part, meaning this could all be filled in, and just this little teeny space here, it's still considered a washer. This entire shape must be completely adjacent and touching that axis of revolution for it to be a disc. Okay, so what's the setup? Volume by discs perpendicular to the x-axis. Okay, so let's take something pretty basic. Remember, perpendicular to the x-axis means that our function will be in the form of y equals, and when we begin to integrate, it will be dx. So here it says, let f be a continuous, non-negative function on this closed interval from a to b. We're going to assign the letter r as the region that is bounded above by f of x and below by the x-axis. So in this case, they're just sticking pretty basic. So this is a top minus bottom. The top is going to be f of x and the bottom will be y is equal to 0. And then we have our sides, which is x is equal to a and x is equal to b, which are the bounds, and they're just saying that this continuous region is going to keep going in either direction. My bound is this vertical line and this vertical line. And what we're going to do is find the volume of the solid that is revolved around the axis of revolution, which will create this region R about the x-axis, okay? Which in this case, as I stated before, is where y is equal to 0. Okay, so first of all, this is what we're looking at. We have our function y is equal to f of x, which is right here. And then we have our x-axis, which is where y is equal to 0, which is right here. And we're going from A to B. Okay, and you notice the shape is adjacent to the axis of revolution. It is touching, completely touching. So then this region R, as it is revolved all the way around the x-axis, 360 degrees, creates this bell-like shape. So if you notice here, this is your axis of revolution, right here. Okay? And you have f of x, which is your top minus your bottom. So it's this minus this. Okay, and what's going to happen is it's going to create this slice right here, which is a circular shape. And what we'll have here, we'll just call this R for the radius, R. And in this case, this radius is going to be the top minus the bottom. Okay? So if we have this circular shape, which would be our disk like this, I'm going to take this out, sketch it right here. Okay? And we have our center, and this is our radius. This radius is equal to our f of x, which is this function that's on the top, because technically it would be top minus bottom, but our bottom is 0. So what we're doing is we're calling that R our f of x function. So it says that we can solve this problem by slicing. So this is our slice. And for this purpose, observe that the cross-section of the solid taken perpendicular to the x-axis at this given point, x, is a circular disk, so this disk right here, okay, of radius f of x, because that's our function, because the radius is going to be the top minus the bottom. Okay, and because this cross-section is a disk shape, the application of this formula is called the disk method. Okay, so what we have here is the volume, and if you recall, the area of a circle is pi r squared. So this r right here is our function, f of x. So I'm going to make that substitution. So the area is equal to pi f of x squared. So this is just one small piece. So if we integrate, we're actually going to get the volume of this whole thing. So our volume is going to be equal to pi times the integral from a to b of f of x squared dx.